This video contains the solution for AP Calculus. This is the 2010 test, problem number 6. It's a Taylor series problem, as problem number 6 usually is. But it's given in an unusual form here. It's given as a piecewise function. So let's take a second to look at this. It's this everywhere except for 0, because this is a 0 over 0 there, and then they're just defining it at x equals 0. It is this negative 1/2. So it's negative 1/2 at x equals 0, and it's this everywhere else. So let's see. The function f defined above has derivatives of all orders. Let g be the function defined by g of x is equal to 1 plus the antiderivative from 0 to x of that function. All right. Part A. Write the first 3 non-zero terms and the general term of the Taylor series for cosine, nothing to do with this, about x equals 0. And use the series to write the first 3 non-zero terms and the general term of the Taylor series for f. Okay, so first we need to do the series for the cosine function. Cosine x is equal to, that's the even one, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, dot, dot, dot. That's the first 3 non-zero terms, and then the general term would be x to the 2n over 2n factorial, and the sign flipper, we would have started at n equals 0 here to get this, so that would be negative 1 to the n. That's the general term. And for the second part of this, they want us to use that to write this series. Well, let's see. If I take the cosine series, this series, and subtract 1, that's just going to remove the 1, right? And then if I divide by x squared, that's going to knock every exponent down by 2. So let's see. F of x is equal to, the 1's gone now, so I have minus, and then we're taking x squared out. We divided out x squared from every term, so that gives me 1/2 plus x squared over 4 factorial minus x to the 4th over 6 factorial would be the next one. And then let's see if we can do a general term here. Looks like it's, if we work from this one, what happened here? We did x to the 2n minus 2. We subtracted 2 from the exponent over 2n factorial. And I think we still have our sign flipper. Did we start with n equals 0 here? If we did that, gives us x to the negative 2. No, that doesn't really work because, let's see, where would n have to start at here? This is the, if I plug in 1, I get x to the 0, and that would actually give me the first term. So let's say starting at n equals 1. You just make a little note for them there. I think probably you get full credit without having that, but just to be clear, that's the n equals 0 doesn't give us a viable term there. Okay. Part B. Use the Taylor series for f about x equals 0 that we just found in Part A to determine whether f has a relative maximum, relative minimum, or neither at x equals 0, and then give a reason for your answer. Well, let's see. If it's got a relative maximum or minimum, then its derivative would be 0. So let's see. The derivative of this would be, that would be gone. It would be, this is x squared over 4, so the derivative of that would be 1/2 x, right? Minus, this is x to the 4th over some large number, so that the derivative of that would be 4x cubed over 6 factorial, and so on and so on. And when you plug 0 into that, we get 0 because every single term in this is going to have an x in it, so that means we have a critical point, right? Because the derivative is 0. So it looks like it could be neither, I guess, if it were like a saddle point. So let's go a little further and figure out what about the second derivative. The second derivative of this function is 1/2 minus 12x squared over 6 factorial, whatever that simplifies to, and so on and so on. And when you plug 0 in, the 0 knocks out every single term that has an x in it, which is every term except for that. So the second derivative is 1/2, which means it's concave up. So let's see. If the derivative is 0, horizontal tangent line, and it's concave up, this must be a minimum at x equals 0. So there's your justification right there. Let's see. Now, part C, they want us to write the 5th degree Taylor polynomial for g, which is 1 plus the antiderivative of this one, just with x's plugged in, about x equals 0. So let's see. If you want to take the antiderivative of a series, you just take the antiderivative one term at a time. So let's try to do that. First of all, don't forget the 1 here. It's 1 plus, and then we're taking the antiderivative of this. And I guess I should have held off on the plus there. Antiderivative of that is minus 1/2 x. Antiderivative of this term, bump the exponent up 1, divide by the new exponent, so that's plus x cubed over 3 times 4 factorial. And then bump the exponent up 1 and divide by that new exponent. So I think that's the 5th degree polynomial. So that's part C done. And then in part D, the Taylor series for g, when evaluated at x equals 1, is an alternating series with individual terms that decrease in absolute value to 0. Why are they saying that? That's the information you need to know to guarantee that the error bound is the next term. So they want us to use the 3rd degree version to estimate g of 1. So g of 1 is approximately equal to its 3rd degree approximation. That'd be 1 minus 1/2 plus 1 over 3 times 4 factorial is 24. And that's, let's see, 1/2 plus 1 over 72. 1/2 is 36 72nds. That's 37 over 72. And explain why this estimate differs from the actual value by less than 1 over 6 factorial. Well, explain. So since the terms approach 0 and g of x series alternates, you have to say both of those things. This is worth a point right here saying this. The error is the next term. So what is the next term? Next term is this. And we're plugging 1 in, right? So the next term is 1 over 5 times 6 factorial, right? So that's the maximum error. And that is less than 1 over 6 factorial, right? If you multiply, if you make the denominator of a fraction bigger, it makes the fraction smaller. So this is clearly less than that because they have the same denominator but for the factor of 5 there. So there we go. It was the next term